We'll proceed in innovative approach in calculus. Innovative approach in calculus. What we have done till now. I mean, what we have invented till now. That is the innovative approach. That is not mentioned in any of the book. That is innovative approach. What is the innovative approach that we have seen in calculus? One of the big thing what we brought into the picture is the Lagrange multiplier, alternative to the Lagrange multiplier. Why I am saying this is very important? Because we are bringing into the picture the concept of directional derivative. Concept of directional derivative. Directional derivative is a concept that can be used in many things in calculus. Whatever Lagrange is saying, it is highly local to the problem of maximization, and that is also bringing in kind of a new extra variable, that is lambda. So it is not considered as the very perfect solution. Okay, so Lagrange variable is not considered as very perfect solution in a way that it is how we solve a problem. So there is always a concern. There is always a kind of anyone you'd be kind of he would be looking for it curative. So anyone would be curative to know that how we solve a problem. I'm not talking about mathematics only. In real life, to anything, how we solve a problem. If I get a problem, how I solve a problem. Okay, I am standing on a road. I am standing on a road. That is a junction point. Normal question, right? Means there on road I am standing, and if I am standing on a road, then there can be two way I can see the traffic. One side, left side, and right side. Now consider that the point I am standing is a junction, and there are 20 roads coming from this side, they are meeting at the junction. Now, how I can cross this junction? That is a question mark. How I can cross this junction? Can a person can see 20 direction in one go? Not possible. A person cannot see 20 direction in one go. What is other solution? Other solution is to minimize the complexity. Now I have to make sure that which all road have red signal. If there is a road, certainly there will be signal, and which all road now the traffic is facing red signal. Now certainly the traffic would not come from that side. If that is the case, then I have to focus only on the region where traffic is coming. Means I am minimizing the complexity. What is need of looking all around always while crossing the road? First of all, someone should not cross the road when there is traffic going on. That is anyway discouraged. But still, if I am trying to cross the road when traffic is there, vehicle is moving, and that junction has 20 sides, from there vehicle can come. Now the scenario is that I have to minimize the complexity. How I can minimize the complexity? That is the trick used. Now the Lagrange multiplier, it is something like it is growing in complexity. It is bringing lambda and this and that. So many calculation it is doing afterward. Nothing is required. If we are trying to find out maximization, minimization of an algebraic equation based upon some constant line, constant curve, based upon some constant line, some constant curve, then no need to bring in Lagrange multiplier lambda, not required. If we understand the concept behind the finding the maximization, what we are talking here? We are talking that if I need to find maximization, minimization, with a constraint, then that constraint is nothing but directional derivative along a vector. This is what we saw. Okay, what we have seen, we have taken example of production or profitability. We have taken example of production or profitability. In a company in a company the production in the company is dependent upon two raw material. How much raw material is is given in the production of the product, that is dependent upon it. There is a material called A, there is a material called B. Means there are two items. Okay, if production is going on, if production is going on if production is going on, then its production is dependent upon two materials. One is of type A, one is of type B. Type A has X items, X number of item, quantity, amount. It is pushed into the production. Type B has Y amount that is pushed into the production. Now, the production is algebraic equation x to the power 2 by 3, y to the power 1 by 3. That is the production. Production is x to the power 2 by 3 into y to the power 1 by 3. If that is the case, then when production would be maximum? What is the value of x and y when production would be maximum? Certainly when x is infinite and y is infinite, then production would be maximum. Now company is purchasing item A and B. Those are the raw material to make the production of some product. Now this raw material is purchased from outside. If they are purchased from outside, then A item, which is X in number, per unit it costs alpha dollar, and per unit B, per unit it costs beta dollar. If that is the case, then alpha into X plus beta into Y is the net amount company is paying to purchase the raw material. That is limited. Certainly it will be limited. That is less than equal to 3. 3 can be in $1,000, in $1,000,000, whatever it is. That should be less than equal to 3. That is under question mark. That is under kind of a constraint. Following this constraint where x, now alpha x plus beta y less than equal to 3. Now tell me what is the maximum production company makes when production equal to x to the power 2 by 3, y to the power 1 by 3. That is the scenario when the production would be maximum. If there is no constraint, then when production would be maximum? That is the question. If there is no constraint, when production would be maximum? dp by, if p equal to x to the power 2 by 3 into y to the power 1 by 3, dp by dx, that is the variation in the production that is seen when there is a variation in the x. dp by dy, production variation with respect to variation in y. Setting dp by dx to 0, dp by dy to 0. If I set dp by dx equal to 0, I get some value of x and y, some algebraic relationship. I set dp by dy equal to 0, I get some relationship. If I see these two equations, if there are two independent variables and there are two equations, certainly someone can find the value of x and y. In that scenario, those are the value. Value can go beyond one value. It can go with multiple values. In that sense, at those values, the production is extrema. Either it can be maximum or it can be minimum. Without constraint also, a person can find that what is the maxima, what is minimum. But here idea is against a constraint, again a constraint, person has to find what is maxima, what is minimum. As I explained, if this problem comes to mathematics, then mathematics would try to mold it into mathematics. Mathematics has a different way of grammar. In that grammar, first it will try to convert it. So in mathematics, there is a grammar of independent component, dependent component, then its complexity in a sense that it is what dimension it is, 2 dimension, 3 dimension, and what is the line, what is the curve, and then what is differentiation, what is partial differentiation, what is the vector form, and what is the different coordinate system. So many things. The mathematics would try to bring it into its own grammar. When problem is given to the mathematics, anyone can solve the problem through any science. It's not restricted that mathematics is the only thing which would solve this problem. But if this problem comes to mathematics, then mathematics try to mold it into its own way. Now, mathematics is seeing this is a three-dimensional problem where x and y are independent component and productivity is z component. Okay, so z or function over x and y. Small f braces x comma y braces close fxy. Z equal to fxy. Now z equal to our productivity equal to or fxy equal to x to the power 2 by 3 into y to the power 1 by 3. When this will be maxima or minima. So simple. Dz by dx equated to 0. Dz by dy equated to 0. Now whatever xy comes, there it will be maxima or minima. Here, if someone really differentiate and finds the value, it will come as x equal to 0, y equal to 0. At that point, it is minimum. At that point, it is extreme point and it is minimum. So if I see this is x-axis, this is y-axis, this is x-axis, this is x-axis, this is y-axis, this is z-axis. Now, x-axis and y-axis and z-axis. If that is the scenario, then x to the power 2 by 3, y to the power 1 by 3, that is productivity. Now each point, now I can take many x comma y point on this xy plane, many. For each x comma y, I have z value. For each x comma y, I have z value. When x comma y equal to 0, 0, then it is 0. And then x comma y will always be positive. Then first quadrant one. So this is first quadrant, this is second quadrant, third quadrant, fourth quadrant. In the first quadrant, beginning from the 0, it will start rising because x to the power 2 by 3, y to the power 1 by 3. It would start rising the way x and y is growing. The way x and y is growing, it will start rising. In that scenario, if it is start rising, then in that scenario, it would not reach maximum ever. Go beyond to infinity, it will keep increasing. It is not like it will go up and it will come down and then it will go up, it will come down, maximum, minimum. It is not there. It is keep on growing. In that way, constraint makes sense. What is the constraint here is x plus y less than equal to 3. Now I have to pick x comma y. I can pick any x comma y, but now I have to pick x comma y. This is the line. This is the line. If this is x-axis and this is y-axis, then this is the line called x plus y equal to 3, which make interception on the x-axis as 3 comma 0, interception on the y-axis at 0 comma 3. This is the interception. If that is the case, then x comma y has to be below this region, below this line, less than this line. In this region only I have to find all x comma y. That is the constant. I cannot go beyond it. And I cannot come beyond it origin because x and y has to be positive. So constraint line means below that line only I have to choose x comma y. Now if I see z fxy graph, then z is growing. Z is growing, keep on growing. But here there is a bar. Now z I have to if I take this cut, if this is x comma y line, if this is x comma y line, then I go like this and create a wall and it will cut down the whatever it is beyond that fxy. Underneath only I have to find what is. Certainly maximum will be on this line only. Where on this line the maximum is. Otherwise there can be scenario that maximum can be here only and then it goes down, come up, goes down, then finally it is hitting x plus y equal to 3 line. That also can be this scenario. If that is like that, then someone has to try dz by dx equal to 0 and dz by dy equal to 0. Then try to find x and y, set of x and y points where it is maxima or minima and means extreme point. Then check against the equation, it is maxima or it is minima. Okay, but in this scenario it is keep on growing. Looks like maxima will happen only on the line. So Lagrange is saying that make the cross section. Make the cross section means contours. So at height 1, if I draw this fxy graph and at height 1, I make a cross section. In other way, if height is 1, x to the power 2 by 3 into y to the power 1 by 3 is the productivity. Productivity is 1. X to the power 2 by 3 into y to the power 1 by 3 equal to 1. If that is the set scenario, then what is the value of x and y? If that, what is the different value? I keep on repeating video by video. This is very important. X comma y, what is the set of x comma y points I take, then it will be equal to 0. Like circle x square plus y square equal to 1, that is a circle. If I choosing x and y point like 1 comma 1, x is 1, y is 0, then also it is 1. X is 0, y is 1, then also it is 1. Like that, I have to select x and y points when it will be 1. In that scenario, it will be a circle. Since like that x to the power 2 by 3 into y to the power 1 by 3 equal to 1, I have to select some points. That will be a curve on this xy plane. This curve should not go beyond x plus y equal to 3. If this is x-axis and this is y-axis, then this is x plus y equal to 3. Whatever contour, I am drawing a contour for the height 1. This contour is like this. Height 2, this contour is like this. Height 3, it is touching this. Height 4 is crossing this. It should touch maximum. It should not cross it. That is the idea. Now question arises is that if it touches, if Now question arises is that if this is consider this is the curve and this is x plus y equal to 3, and at moment it is touching it, the moment it is touching it, at that moment if I draw a gradient that is perpendicular to this graph, and then gradient of this line that is also perpendicular to this line, gradient of this line, gradient is a vector, gradient vector for this line is perpendicular to this line. Gradient vector for this circle, for any curve, is perpendicular to the curve at that point. That is the gradient vector. This is tangent vector. This is gradient vector. This is a line, then itself it is a tangent. Then gradient vector will be perpendicular to it. If this line, if a contour means at a particular height. If I set the height fixed, then xy would start changing on the xy plane and it will draw a curve, that is the contour, because it has to satisfy the equation. Now if this is the curve and it is touching xy line, x plus y equal to 3, at that moment the gradient of this curve and gradient of this line, they will be parallel to each other. So Mr. Lagrange is saying that gradient vector of the contour curve equal to lambda into gradient vector of the constrained line, because two vector are in same direction possible, but they may be different in magnitude. So lambda is provided to settle it down. That is Lagrange multiplier. When we solve any problem, we try to minimize the variable, not maximize the variable. We are introducing new variable, and at the end we will land up into Lagrange equation, Lagrange this, Lagrange that. So many things will start coming. So many calculus you will find in the book for the Lagrange. Beyond that, not required. What we are trying to find is maximization, minimization. Maximization, minimization problem. If I have a line, if I have a curve and I try to find maximum for the curve when it is reaching the maximum, then this, can we see, this is the point we are reaching the maximum. But this point we are reaching the maximum because we are comparing with the x-axis. If this is the x-axis, with respect to x-axis, this is the point where it is maxima. But this is not true if axis is here. If x-axis is this, then maximum is here. If x-axis is this, then maximum is here. If x-axis is here, then maximum is here. So maximization, minimization depends upon on which axis we are trying to do. Blindly, we cannot say dy by dx equal to 0. I found the maximum. We found the maximum with respect to x-axis. We are trying now, what we are trying to do? If x plus y is a line, if x plus y is a line, then this corresponds to a vector, an axis. We are trying to find this curve maximization and minimization against this line. If this is a curve with equation y that is equal to fx, and this line is a kind of vector u, then we are trying to find dy by du. If this line is x-axis, then we are trying to find maxima or minimum, then we are trying to find dy by dx equal to 0. There we find maxima or minimum. If this vector is u vector, here if it is x-axis, it is I vector, I unit vector. If it is u vector, we will try to find the unit vector of it. Consider u is unit vector, then for this y, fxy, for this fxy, we are trying to find maximization, minimization along the vector u. dy by du equal to 0. dy by du, this is our proof. This is very solid, the most logical. With this, we can climb to sky, because we are talking about generalization in differentiation. That is a big thing. And what we see dy by dx, it is mere a special case of generalization of the generic dy by dx. We are talking about generic derivative. Generic derivative, it is a very big thing. It is also mentioned as directional derivative along a vector. Actually, we are trying to find maximization along a vector, that is the line x plus y equal to 3. And that maximization of a algebraic equation, that is x to the power 2 by 3 into y to the power 1 by 3 equal to some constant. For that constant, we have the contour diagram. Please support us. +91 is India country code 9483160610. +91 is India country code 9483160610 is our telephone number. Please do support us, it helps. Okay, so in that scenario, it helps in people in learning. You grasp more if you support. Anyway, so in that scenario, we are trying to find the maximization, minimization of a contour with respect to some vector. What is the vector? Now another area we are entering, how to calculate what is the directional derivative of an algebraic equation fxy along any vector u. Gradient vector of fxy, gradient vector of fxy dot with the unit vector along the vector for which we are trying to calculate directional derivative along. Directional derivative along a vector. Along a vector, I am trying to calculate directional derivative of an algebraic equation. Then gradient vector of the algebraic equation dot, and then the unit vector of the vector along which we are trying to calculate the directional derivative. So here, what is the vector of x plus y equal to 3 that comes into the picture? This is again our fundamental, and it is not available anywhere. How to calculate how to calculate the directional vector along any line or any curve. If this is the curve, at this point, what is the directional vector? This is the tangentially the directional vector. This is the gradient vector of this. This is the curve. If this is the curve, then this is the gradient vector. Gradient vector is perpendicular to the surface line, curve. This is also referred as position vector. because if this point is x comma y, this is the origin. If this is the origin, then this is considered as position vector xi plus yj. Then whatever we are trying to get the vector along a algebraic curve that is perpendicular to the position vector or perpendicular to the gradient vector. Now question is arising that now I am saying that to calculate the maximum minimum, no need to go for Lagrange multiplier delta lambda, we can find this through the directional derivative along a vector. If I have algebraic equation x to the power 2 by 3, y to the power 1 by 3, and then the constraint line is x plus y equal to 3, then gradient vector of this algebraic equation, that is 2 by 3 x to the power minus 1 by 3 y to the power 1 by 3 I plus 1 by 3 x to the power 2 by 3 into y to the power minus 2 by 3 j. This is the gradient vector of algebraic equation. If this is the gradient vector of algebraic equation, then that gradient vector at any point is like this, perpendicular to the surface. All right, I don't mind. That is the gradient vector of algebraic equation. Dot the unit vector of the vector along which we are trying to calculate the directional derivative. So the line is x plus y equal to 3. Line is not vector. Line is line. How to calculate vector equation of a line, vector equation of any curve. This is our fundamental. Please support it. This is not available in any of the book. How to find the vector representation would be available, but not through this approach. How to find the vector representation of any line, any curve. Now, we know that if I take position vector, consider this circle, and there is a point called x comma y. If there is a point called x comma y, then from center, if I draw a line, this is a position vector. If you see, position vector is perpendicular to the surface everywhere. If that is the case, then gradient, if that is the case, then gradient of this position vector is the vector along the line we are trying to calculate. This is vector we want. Or if there is a line, then this line can be represented as what vector? If that is the scenario, then this line I can represent as a position vector. Any point x comma y, any point x comma y, consider this is origin, this is origin, this is origin, and this is the line. If I take any point here x comma y, okay, if this is the origin, this is the line, then from the origin, if I go, if from origin, if I draw the line, this is the position vector. I would repeat it. This is origin, this is origin, and this is the line. For this line, I have to find equation is x plus y equal to 3. I have to find vector notation for it. This is the origin. If I take any point x comma y, then from origin, if I connect this becomes position vector. Can you see this position vector is this becomes position vector at that point. Okay, if this is position vector, if I draw gradient of this, then certainly it will come along the line. This is what we want. Position vector itself is a vector. Gradient of it will be a vector. That is what we want. If I want vector along the algebraic curve, then first I find the position vector and gradient of position vector, that is gradient is perpendicular. Always this is what we have seen. If I have a vector, if I calculate gradient, it will be perpendicular to that vector. So if I have a position vector, if I calculate gradient, it will be this vector. This is what we want. Like this, if I have a position vector here like this, if I calculate gradient vector, it will become parallel to this. This is what we want. Now what is x plus y equal to 3? Now if I take any point on this line, that is x comma y, that is xi plus yj. Now we found the position vector xi plus yj. Just find the gradient vector, you get the vector. Simple, right? Now x plus y equal to 3, y equal to 3 minus x. then xi plus 3 minus xj is the position vector. Let's find the gradient vector. Let's differentiate it. It becomes I minus j. Earlier it was xi plus yj. Y equal to 3. This is our way. This is not available anywhere. Please do support us. Okay. So xi plus yj. Xi plus yj is the position vector. If I differentiate it, calculating the gradient of this, I won't say gradient vector because xi plus yj position vector is the vector itself. If I further differentiate it, it becomes 90 degree from it. If that is the case, then it is now xi plus yj, I plus dy by dxj. Dy by dx, it won't be 0 because y is dependent upon x. It is 2d. Y equal to 3 minus x. I minus j is the exact vector notation of this line. If that is the case, then gradient vector what we had calculated x2 into 2 by 3 x to the power minus 2 by 3 into y to the power 1 by 3 I plus 1 by 3 x to the power 2 by 3 y to the power minus 2 by 3 j dot product with I minus j unit vector. I minus j by square root of 2 equal to 0. Now it will give the maximum minimum. If someone settle down, then it will become 2 by 3 x to the power minus 1 by 3 y to the power 2 by 3 equal to 1 by 3 x to the power 2 by 3 y to the power minus 2 by 3. It will settle down. Y I can take this side, x I can take that side. Then it becomes 2y equal to x. What is difference between Lagrange way and our way? Our way, Lagrange directly calculating the gradient vector. That is pretty easy. And then lambda you have to bring. But if you bring a new variable, it becomes a nightmare. It is far simple to calculate the vector of a gradient vector to represent some line, some curve as a vector notation. But that is difficult. Our invention is there. So how to represent any algebraic curve as a vector notation? We invented it because we need it. So at that moment, now we can calculate it. It is far easier, far easy. Okay, we will take more cases in this sense because there is another world to calculate the vector along a curve. Can someone think about calculating a vector along a sphere 3D, 4D, 5D, 9D, 10D, where we will, if I have a 3D, okay, I have bigger 3D. This is 3D. Okay, if I have if I have 2D circle, if I have 2D circle, then how someone can find the vector representation of algebra? That is this line. Now, if that is the case, if I have 3D ball sphere, then this is the vector we are trying to find. At any point, if I try to get this vector can be all along. Can you see this? I cannot say this is the only vector that is along the surface. This can be all vector 360 degree along the surface. Okay, if I have something like this shape, I don't know what is the algebraic equation for this, but we are trying to find a vector that at the surface, it is along the surface, but again it will be 360 degree. This is 3D. Now this can be considered as an assignment. This can be considered as an assignment that can someone find the equation of a vector along the surface in 3D. Okay, through the fundamental what to give any point on the 3D, I can represent it as xi plus yj plus zk, any position vector or point x comma y comma z. Okay, so that someone can try. It's not very difficult, but as I say, mathematics is game of following things step by step. If you miss the step, then you will be lost in the space. But if you follow step by step, then it is pretty much into the control. So we will proceed with the case study. Please do support us. +91 is India country code 9483160610.